Now, if we look at we are going to look at what is called as an interface mass transfer. So, let us take an interface, so any interface. So, this is a very classical mass transfer concept, and it is applicable here also. So, let us take we have air and water, that is two interfaces and applicable to all interfaces, but you have to understand there are assumptions involved in this. Assumptions are based on what we discussed in the previous slide about the boundary layer and beyond the boundary layer what exists. So, based on what we discussed, if there is an interface, what we are assuming is that there is a region. So, let us make this interface bold line, and there is a region on the side of the water and on the side of the air in which there is a resistance. Okay. All the mass transfer resistance is in this why have I separated this with this bold line? Anybody? Huh? What is different? The phase is different. So, we talked about that if diffusion is happening, for example, the diffusion here is very different from diffusion here, that is one thing. Second, is there a second reason? So, if I want to write down the flux, if I am looking at something say from water is evaporating into air, okay. There is a chemical say benzene is there in water and it wants to evaporate into air. Okay. Now, based on our discussion, what will if I plot the concentration, the gradient, what will it look like here? What are the different possibilities? So, it is very tricky thing. So, first you have to decide if I am writing a gradient, I need two numbers, right, two numbers which are measurable. So, where will I measure the water? I have to measure it somewhere, right, where will I measure it? So, I give you a beaker and say there is benzene in solution of benzene and water in the beaker, and I am saying draw this gradient, initial gradient at least. So, when the beginning of the process, for which I need to know the measurement of concentration of benzene. Where will I measure it? I have a beaker, where will I measure? What is your natural tendency? Let us forget about concentration. Let us say if I ask you to measure temperature, where will you measure? What will you do? You will just put something here, middle. The middle, is that enough? If I take a probe and put it here and taking a measurement somewhere here, how many of you think it is okay? When you are taking any measurement, I am sure you have taken measurements of temperature in water in your class somewhere. If I do this, is there any question? What is the question that you will ask? This goes to monitoring. We are going back to our other this thing also. Huh? What is the question that if I report a value here, I just stick it in like this and then I say the temperature is such and such. Do you have any question, doubt? Huh? Temperature is uniform or not? Yeah. So, why am I doing it here? Why not do it here, here, here? There are 100 places where I can choose to do it. Why am I doing it here? You have an answer? So, I can do it at 100 different places. Yeah. So, this is I think at the crux of the problem, this definition of the problem itself. The system, see in engineered systems I can make it, I want to do something, therefore I can arrange the system to be in a certain manner. The environment does not care, it will do whatever environment wants, so you have to follow it. Okay. So, this is very important, this is a problem in the environment. So, what is the easy way out? If you want to make sure it is uniform, you mix and this entire thing becomes uniform. So, it does not matter where I take this measurement. So, if you start with this system, is there still an interface mass transfer resistance on the water side? So, if I do this mixing, how will I plot this? What will this plot look like? This is the scale of the concentration. It's a concentration scale on the x axis. Okay. Sorry, this is z. This is the scale. This is the scale of concentration, both rho A1 and rho A2. What will it look like? When it is well mixed, what is it? What we mean by well mixed is uniform concentration, which means it will be a straight line. Okay. How far will it be a straight line? It will go, it will come here, and then at this point it will start going down. So, this is the gradient, and the reason is we have defined that there is a small region very close to the interface where all the resistance to mass transfer exists. So, we are stirring the water. So, if we do not stir the water, what will this look like? It may look like this. The gradient may extend to a long distance. Okay. But if I am stirring the water, if I stir it very well, this thing keeps moving. I can keep getting constant value for closer and closer to the interface. Okay. So, if I keep on stirring very hard, there is a limit to it. This distance, let us call it as delta. This delta keeps reducing as my mixing efficiency keeps increasing, but at some point it will stop. It cannot go beyond it, because at the surface interface, because of interfacial tension, you still cannot have, there is friction offered by the other interface there. It will not go all the way to the, you will not get a profile which goes all the way into this thing. It is very difficult to get this. Theoretically, people have seen that there is a region, even however small it is, there is still a small resistance that exists there. What we mean by resistance is fluid does not mix well. It slows down there, and therefore the resistance is higher, mass transfer resistance is higher. Okay. What is the concentration on this side? On this side. So, let us say now that we have we will mark this line. Let us say that I have let me redraw all of this. This is my profile. We have established that this is the profile here. What is it on the other side? So, I will write this as rho A2, and this one, what is this one? I will label it as rho A2, I will call it as rho A2 interface, because it is at the interface on the water side. The gradient is continuing, mass transfer is continuing in this direction. So, what will what will be the value, what will happen here at the interface? Here is the molecule is in the water, it is travelling, it is being brought into the near the interface, and the interface it travels here and it comes to the interface. Then what happens? It has to go to the other side, it wants to evaporate. What will be the concentration on the other side? You do not know, but can you make an assumption? What can it be? Truly we do not know, but there is an assumption. Can you make an assumption that what could it be at the interface? When you have, no, steady state, system is steady state, that we will come to that, but more than that, what is the assumption? So, if you do not know a concentration of something, what can you assume? 0, but it is not 0. So, this is another thing, this is a steady state process. So, there is no this thing of time here. So, material is here, it is going here, it is constantly it is going, it is continuously going from one end to the other end. So, it is a steady state process, which means it is not 0. Equal rho A2I. So, this is a question, is it equal to rho A2I? Let me give you a very simple example. You have, forget about benzene and all that, I have water. I have water, everything is water, right. What is the concentration of water at the interface in the air? Liquid water is standing on the interface, there are some molecules of water in the vapor phase. What is the relationship between this one and that one? Is it the same? What is it? Huh? Less than how much? So what is there a way to find out? Saturation?
Concentration of water.
What is that? It's equilibrium saturated vapor pressure. So what is it? So what are we assuming here?
It's in equilibrium.
It's in equilibrium. So what we assume, what the best we can assume is that this is in equilibrium with whatever is there on the other side. So it's liquid, gas liquid equilibrium, or in this case it is air water equilibrium. In case it is Henry's constant in our case. For water it is very obvious, right. You do not see the water is there on interface, what is on the other side is vapor pressure, that is all. Amount of water vapor is changing, but it stops there, it will stop there. So very close to it, we are assuming it to be very, very humid, and this is an assumption we are making. And so this theoretically, the assumption is valid because theoretically nobody knows where the interface is. We are never going to be able to go and measure the interface. It is a theoretical assumption. Okay. We do not have any probe that is at the resolution of molecules that we can go and see yet. We do not have it yet. Maybe we will invent it in a few decades, I do not know. So this concentration here is, we will mark it on this side, we call it as rho A21I on the other side of the interface, and then this also will go like this. So we assume that the air is well mixed, and there is a small region where the mixing does not reach. We will mark it with a different color, we will mark it with purple. And so this number is 21I, and this number here is A1. So we are assuming that this is all well mixed, and this is all well mixed. Now this thickness and this thickness, let us call it as delta 1 and delta 2, need not be the same, will not be the same usually depending on what is there. For example, if you are in a lake exposed to air, lot of wind on the air side, what is on the water side? We are not mixing anything, and there is little bit of turbulence on the water side. So if I have a lake surface, there is a lot of wind, but on the water side this is pretty much this, yesterday we discussed that there is a small region near the surface where there will be some amount of mixing, but this is nothing compared to amount of mixing happening in the air side. Okay. So the boundary layers on the air side and the water sides are very different, therefore the mass transfer coefficients are very different. Yeah. So here is where we invoke a steady state assumption. So the steady state assumption is as follows. We have Na equals, so the resistance here corresponding to this phase is called as, we call it as Ka1 2, and the resistance on this side is Ka2, sorry, this is Ka21 and this is Ka12. What we are saying is Ka21 into rho A2 minus rho A2I equals Ka12 into rho A1I minus rho A1. If the overall gradient is in this direction, mass transfer is happening in this direction from the water towards the air. If we invoke the steady state assumption, this is true. What does steady state assumption mean at the interface? When we say steady state, if you invoke the steady state mass balance is rate of accumulation equals rate in minus rate out. Steady state means rate of accumulation is 0, which means there is no accumulation at the interface. Whatever is coming from one side is getting transferred to the other side, nothing is staying at the interface. This is usually true even if it is not true, we will not know until we actually measure it, but this is very good assumption to make for this particular this thing. There are very few cases where there is accumulation in the interface, that happens a little bit, but special cases of that. So, here we have a problem. So, let us say I want to take this, I can use either of these equations to estimate the flux. So, what it means is that I can either use this, the water side equation or the gas side equation, either one is fine. It will give you the same flux, it should give you the same flux. But the problem I have now is this number very difficult to measure. Likewise, this number is very difficult to measure. These two numbers are not easy to measure, but I do not even know where the interface is. For example, if I ask you to measure the interface temperature at air water interface, I need a probe which is of the same dimension of the interface. Now, I am not even sure how thick is the interface. Interface is a, you know, you have molecules of liquid and suddenly there are molecules of air, it starts moving and it's about the thickness of a molecule probably. This is my guess. Okay. If you do molecular dynamic simulations, they work like that. They work at the level of a molecule. So, the thickness of the interface is exactly the thickness of a molecule. Now, I have to find a probe for that. Now, if this is the interface, my probe looks like this. The smallest probe you can look at it is micron nanometer thickness, which is never stable, not at all stable. So, if you thermocouples and all that are thick wires, right. This is, I am exaggerating this interface, the probe will probably look like this. However close I go, some of it is measuring the air temperature, some of it is measuring water temperature, I am not really sure. So, I can't rely on this. Forget about measuring concentration at the interface, it's even worse. You can't. When we are talking about gradients in this small region, and this region itself is very small, I cannot really get the interface concentration. So, my only best bet is I can measure this with great deal of confidence and this with great deal of confidence. So, I will stick to this, but if I stick to this, I cannot, I need another equation where I will say rho A2 minus rho A1. With some imaginary k. This is not a legal way of writing a gradient. You cannot write a gradient in water and air because in between there is an interface and you have a thermodynamic equation in between, and that will violate several things. So, we have to express this in terms of taking into account all of these things. So, tomorrow we will derive that equation. The purpose of this is I can measure these two in the bulk phases which are well mixed far away from the interface, okay, like this what we are doing here with without worrying about whether it is accurate or not. We are assuming as long as we know it is fairly well mixed and uniform, we will take that as the bulk concentrations. At the interface we do not care, we will not care, but then we have to incorporate this into that somehow. So, that is the derivation of the equation and we will see that tomorrow.